For most of the 20th century, the world fought over oil, who controlled it shaped global power, alliances, and wars. But in the 21st century, a new resource has taken its place, not buried underground, but etched onto tiny slices of silicon. These microscopic chips now run the global economy, modern militaries, artificial intelligence, and the digital systems that power everyday life. And today, the race to control them has triggered a new kind of geopolitical competition, one that stretches from Washington to Beijing, from Dutch factories to Taiwanese laboratories. This is the story of the global chip war and why the most powerful technology on Earth is smaller than your fingernail. Consider something you cannot see. Without a microscope, a sliver of silicon, smaller than a fingernail, etched with billions of transistors so fine that the spaces between them are measured not in millimeters, but in nanometers, a unit so small that a single strand of human hair is roughly 80,000 of them wide. This object does not look like power. It does not look like politics. It does not look like anything at all. And yet this chip, this semiconductor, now sits at the center of the most consequential technological and geopolitical competition of the 21st century. Governments have built entire industrial policies around it. Alliances have been tested because of it. Trillions of dollars have been committed in its pursuit. And in one narrow strait of water in the Western Pacific, the possibility of military conflict has become inseparable from the question of who manufactures it. This is the story of the global chip war and why the stakes have never been higher. To understand why a piece of silicon has become a geopolitical flashpoint, we first need to understand what semiconductors actually do. A semiconductor is a material, most commonly silicon, that can conduct electricity under certain conditions and not others. This property allows engineers to build transistors, the fundamental switches that make digital computation possible. When you pack billions of those switches onto a single chip and connect them with extraordinary precision, you have a processor, a brain of sorts. That brain now runs almost everything: the smartphone in your pocket, the server farm processing your search query, the car navigating traffic, the satellite monitoring crop yields from orbit, the missile calculating a trajectory, the hospital machine monitoring a patient's vital signs. Strip out the semiconductor and virtually every advanced system in the modern world stops functioning. So what happens when access to that resource becomes uncertain? The answer to that question is precisely what has driven semiconductors from the pages of engineering journals onto the desks of national security advisors. Chips are no longer simply a commercial product. They are infrastructure. They are leverage. And in an era of intensifying great power competition, they have become one of the most sought-after forms of strategic advantage on Earth. But unlike oil, which can be extracted from the ground in dozens of countries, the most advanced semiconductors in the world can only be manufactured in a handful of places, using equipment that only a handful of companies can produce. That geographic and industrial concentration is at the heart of everything that follows. The semiconductor industry has, over the past half-century, built one of the most complex and interdependent supply chains in human history. It stretches across continents, through dozens of specialized industries, and depends on a level of technical precision that very few countries have managed to develop at its simplest. The journey of a chip involves 3 stages: design, fabrication, and assembly. Each stage is dominated by different actors in different parts of the world. Design, the intellectual architecture of a chip, is concentrated primarily in the United States. Companies such as Qualcomm, Nvidia, AMD, and Apple do not manufacture chips. Instead, they create the blueprints, the intricate logical structures that determine how a chip will perform. This design work is done using specialist software tools, known as electronic design automation, or EDA, a field where American firms hold a commanding global position. Fabrication, the actual physical manufacturing of chips from those blueprints, is where geography becomes most critical. The most advanced chips in the world are produced in Taiwan and South Korea, by a small number of foundries capable of working at the bleeding edge of what physics currently permits. And then there is the equipment required to do all of this. The machines used to manufacture advanced chips are themselves extraordinarily sophisticated. Photolithography systems, the devices that etch circuit patterns onto silicon wafers using beams of ultraviolet light, are produced primarily by a Dutch company called ASML. Its most advanced machines, which use a process called extreme ultraviolet lithography or EUV, are so complex that they contain hundreds of thousands of components sourced from multiple countries. There is no other company in the world that makes a comparable product. ASML, in effect, occupies a choke point that the entire global semiconductor industry flows through when a single Dutch company controls access to the world's most critical manufacturing technology. What does that mean for a country that cannot obtain one of those machines? It means, in practical terms, that no country can independently build the most advanced chips without either purchasing from ASML or finding an equivalent capability, something that, despite billions in investment, no rival has yet managed to do. The final stage, assembly, testing, and packaging, takes place largely in Southeast Asia. In countries like Malaysia, Vietnam, and Thailand, These nations play an essential but often overlooked role in getting finished chips into the consumer devices and industrial systems that depend on them. This supply chain is a marvel of global economic coordination. It is also, as recent years have demonstrated, a source of profound fragility. Of all the actors in the global semiconductor landscape, none is more consequential or more geopolitically exposed than Taiwan Semiconductor Manufacturing Company, known universally as TSMC. Founded in 1987 by Morris Chang, TSMC pioneered the concept of the pure-play foundry, a manufacturer that produces chips designed by other companies, rather than developing its own. This model proved transformative. It allowed Fables's chip designers in the United States and elsewhere to innovate rapidly without bearing the enormous capital costs of maintaining fabrication facilities. And it allowed TSMC to focus entirely on the science and engineering of manufacturing, which it has done with extraordinary success. Today, TSMC manufactures roughly 90% of the world's most advanced chips, those produced at process nodes of 5 nanometers and below. No other company, anywhere in the world, has demonstrated the ability to manufacture at comparable scale and quality. Samsung in South Korea competes at the frontier, but trails in yield and output. Intel in the United States has invested heavily to close the gap, but remains years behind in the most advanced nodes. TSMC's dominance is the product of decades of accumulated technical expertise, institutional knowledge, and capital investment. Its engineers have solved problems that companies with far larger resources have not. That knowledge does not reside in a building. It resides in people, in processes, in a culture of precision that has been built over years. This creates what strategists have called the Silicon Shield, a concept suggesting that Taiwan's indispensability to the global economy provides it with a measure of protection. The logic runs that no major power, not even one that sought to annex Taiwan by force, would want to risk destroying the infrastructure that produces chips on which the global economy depends. But is that deterrent as robust as it sounds? And how long can a strategic asset of this importance remain concentrated in one island of 23 million people, located 90 miles from mainland China? These are not hypothetical questions. They are the questions driving defense planning in Washington, Tokyo, Brussels, and Seoul. To understand how semiconductors became a weapon of statecraft, it is necessary to understand the evolving relationship between the United States and China, and specifically, the moment when Washington concluded that commercial competition had become a national security threat. For most of the late 20th and early 21st centuries, the United States and China were deeply integrated in the global technology supply chain. American companies designed chips, Taiwanese companies made them, Chinese companies assembled products, and American consumers bought those products. The model worked economically for everyone involved. What changed was not the economics. What changed was the strategic assessment of where that integration was leading. Chinese state investment in semiconductor development, expressed most visibly through initiatives like Made in China 2025, signaled an explicit ambition to achieve technological self-sufficiency and, in time, global leadership in advanced industries including semiconductors. From Beijing's perspective, this was rational industrial policy. From Washington's perspective, it represented a direct challenge to American technological primacy, with implications that extended far beyond commercial competition. Advanced semiconductors are not only essential to consumer electronics, they are essential to artificial intelligence, to hypersonic weapons, to surveillance infrastructure, to communications systems, and to every form of military capability that defines 21st century power. A China capable of producing world-class chips independently would be a China that no longer needed to rely on the technology of its primary strategic competitor. Beginning under the Trump administration and accelerating sharply under Biden, the United States moved to restrict China's access to advanced semiconductor technology. In October 2022, the Bureau of Industry and Security introduced a sweeping package of export controls that prohibited the sale to China of chips above certain performance thresholds. What of the equipment needed to manufacture such chips, and critically of the services of any American person working in the Chinese chip industry? The controls also had an extraterritorial dimension. Foreign companies using American technology, software, or equipment anywhere in their manufacturing process, which, given ASML's dependence on American components, effectively means almost every chip manufacturer in the world were required to seek a license before selling restricted items to Chinese entities. What does it mean when a single government can effectively impose restrictions on a global industry simply by controlling key inputs in an international supply chain? It means that the architecture of technological globalization has created leverage points, choke points that can be activated as instruments of policy. And the United States, through a combination of its own industrial position and its alliances with the Netherlands and Japan, controls several of the most critical ones. China has responded with urgency. Huawei, partially blacklisted from the American supply chain, has worked with SMIC, China's leading foundry, to produce domestically designed chips using older fabrication techniques. In 2023, Huawei released a smartphone containing a 7-nanometer chip that surprised many Western analysts who had assumed Chinese capabilities were further behind. The chip demonstrated resilience, but it also illustrated the limits of that resilience. Manufacturing it reportedly required running SMIC's equipment at the outer edge of its rated performance, at lower yields and higher costs than leading-edge foundries. The gap remains, but China's determination to close it and the resources it is committing to that effort should not be underestimated. It is worth pausing to ask why governments, organizations not typically known for speed or technical sophistication, have moved so decisively into what was, for most of its history, a domain left to commercial actors. The answer lies in a recognition, arriving somewhat belatedly in many capitals, that the semiconductor is to the 21st century what oil was to the 20th. A foundational resource whose control confers strategic advantage, and whose denial constitutes strategic leverage. Military applications are one dimension. The precision-guided munitions, autonomous systems, electronic warfare platforms, and command and control infrastructure that define modern conflict are all chip-dependent. A state that cannot access advanced semiconductors cannot field a modern military. This is not a future contingency. It is the present reality. But the strategic importance of chips extends beyond weapons systems. Artificial intelligence, now widely regarded as a potential source of decisive advantage in economic productivity, scientific research, and intelligence gathering, is fundamentally dependent on semiconductor performance. The AI models that are reshaping industries and capabilities require enormous computational power, the kind that only the most advanced chips, particularly graphics processing units produced by companies like NVIDIA, can currently provide. This is precisely why the United States has placed NVIDIA's most advanced AI chips on its export restriction list. The concern is not simply that China might use them in consumer applications. The concern is that access to sufficient frontier AI compute could accelerate Chinese military modernization, intelligence capabilities, and the development of autonomous weapons systems in ways that would directly threaten American strategic interests. What we are witnessing, in other words, is not simply a trade dispute. It is the early architecture of a technology Cold War, one in which access to silicon has become as loaded as access to oil once was. The strategic stakes of the chip war have a concrete and costly economic dimension, one that became impossible to ignore during the supply chain disruptions of the early 2020s when the COVID-19 pandemic interrupted semiconductor production in 2020 and 2021. The effects cascaded rapidly through the global economy. Automobile manufacturers, who had reduced chip orders in anticipation of a demand slowdown, found themselves unable to source the microcontrollers needed for vehicle electronics. Plants were idle. Delivery wait times stretched 2 months. Ford, General Motors, Volkswagen, and Toyota all reported billions of dollars in lost revenue attributable to the chip shortage. In the United States alone, the automotive industry lost an estimated $100 billion in output over the period. The disruption was a demonstration of a structural vulnerability that economists and industrialists had known about in theory but had not been forced to confront in practice. The just-in-time inventory models that governed global manufacturing assumed supply chain continuity. Semiconductors, assumed to be a reliable commodity input, were suddenly revealed to be a critical dependency with very limited redundancy. The defense implications were equally sobering. Military systems, from aircraft to communications hardware, rely on specialized chips that are often manufactured in small volumes by a limited number of suppliers. During the shortage, the United States Department of Defense identified instances where the availability of specific semiconductors was constraining the production of key defense systems. If a pandemic can expose this vulnerability, what might a deliberate disruption, an embargo, a conflict, a targeted cyber attack on a major foundry do? The answer to that question has concentrated minds in Washington, Brussels, Tokyo, and Seoul in a way that decades of academic analysis about supply chain risk had not. The convergence of strategic competition and demonstrated economic vulnerability has triggered the most significant wave of industrial policy in the semiconductor industry since its founding. Governments across the world are committing extraordinary sums to build or expand domestic chip manufacturing capabilities, not because it is commercially optimal, but because they have concluded that the strategic cost of dependence is too high in the United States. The CHIPS and Science Act, signed into law in 2022, allocated over $50 billion in direct subsidies for domestic semiconductor manufacturing and research. The goal is to bring leading-edge fabrication back to American soil for the first time in decades. TSMC has announced the construction of multiple fabrication plants in Arizona. Samsung is building a facility in Texas. Intel is expanding in Ohio and Oregon. The ambition is not to replicate Taiwan's entire semiconductor ecosystem overnight. That is not feasible, but to establish a credible domestic manufacturing base that reduces the exposure of American industry and defense to a single geographic point of failure. The European Union has launched its own European Chips Act, with the target of doubling Europe's global share of semiconductor manufacturing to 20% by 2030. TSMC has announced a fabrication plant in Dresden, Germany, in partnership with European semiconductor companies. The intent is partly industrial to secure supply chains for European automotive and industrial manufacturers, and partly strategic. Japan, which once led the world in semiconductor manufacturing before losing ground through the 1990s and 2000s, has launched a major reindustrialization push. TSMC has opened a facility in Kumamoto, supported by substantial Japanese government subsidies. A domestic consortium, Rapidus, has announced an ambition to manufacture 2-nanometer chips by the late 2020s, a goal that many analysts regard as technically audacious, but whose pursuit reflects the seriousness with which Tokyo now regards semiconductor independence. And then there is China. Beijing has committed hundreds of billions of dollars to its domestic semiconductor industry through a combination of state funds, subsidized financing, and directed research investment. Progress has been uneven. The export controls imposed by the United States and its allies have made it significantly harder to acquire the equipment needed for leading-edge fabrication. But China's domestic semiconductor industry is not standing still. It is advancing in the nodes and applications accessible to it, and investing heavily in the long-term effort to develop indigenous capabilities across the full supply chain, including, eventually, lithography equipment that does not depend on ASML. The result is a global landscape in which semiconductor supply chains are, for the first time in decades, being deliberately redesigned, not by market forces, but by government policy. The era of purely commercial globalization in chip manufacturing is giving way to something more fragmented, more politically managed, and more expensive. No one can predict with confidence how the global chip competition will resolve, but we can map the contours of the most plausible futures and consider what each one implies. Scenario 1. Managed technological competition. In the first scenario, the current trajectory of controlled rivalry continues without major rupture. The United States and its allies maintain their export control regime, slowing China's access to the leading edge. China advances along an independent path, developing capabilities that are competitive in the mid-tier and gradually closing the gap at the frontier over time. Both blocs maintain functioning semiconductor industries, operating in parallel rather than in integration. Trade continues in areas below the most sensitive thresholds. The world bifurcates technologically, not completely, but meaningfully. This is the most likely near-term scenario. It is uncomfortable, costly, and inefficient, but it is stable. It preserves the deterrent structures that prevent open conflict, even as it hardens the fault lines of great power competition. Scenario 2. Supply chain fragmentation. In the second scenario, the pressures of geopolitical competition produce a more complete decoupling of technology supply chains. The world divides into two largely separate technological ecosystems, one centered on the United States and its allies, another centered on China. Each builds its own semiconductor stack, its own chips, its own equipment, its own standards, its own software tools. This outcome is expensive for everyone. Duplication of the extraordinary investment required to maintain leading-edge semiconductor manufacturing is economically irrational, but economic rationality does not always govern strategic decisions. If both the United States and China conclude that the risk of interdependence outweighs its benefits, fragmentation becomes the logical endpoint, even if it comes at enormous cost. Scenario 3. Geopolitical escalation over Taiwan. The third scenario is the most consequential, and the one that analysts hope remains the least likely. Should China attempt to assert control over Taiwan by military means, the consequences for the global semiconductor industry would be catastrophic. TSMC's fabrication facilities, representing decades of accumulated technical knowledge and tens of billions of dollars in equipment, would immediately become the subject of decisions that no military planner, corporate executive, and no government would want to face. Taiwan has its own contingency planning for this scenario. The United States has made clear that it regards the maintenance of the status quo as a vital interest. Japan, which is a matter of hours from Taiwan by sea, has expressed increasing alarm, and the global companies and governments, whose economic futures depend on TSMC's continued operation, have every incentive to ensure this scenario does not arise. But incentives and outcomes are not the same thing. The escalatory dynamics of great power competition have a logic of their own. The fact that conflict over Taiwan would be economically catastrophic for all parties has not made the possibility disappear. It has made the diplomacy around it more urgent. If the most advanced chips in the world can only be made in one place, and that place sits at the center of an unresolved territorial dispute between two new powers, what does that tell us about the stability of the system we have built? The geopolitics of the 20th century was shaped, in no small part, by oil. The countries that controlled it wielded influence disproportionate to their size or population. The countries that needed it built alliances, fought wars, and structured their foreign policies around securing reliable access. The Organization of Petroleum Exporting Countries demonstrated in the 1970s that a cartel controlling a critical resource could hold the entire global economy to ransom. And for decades, the strategic calculus of every major power included, as a central variable, the question of energy supply. The semiconductor is not oil. It is not a raw material extracted from the earth, subject to depletion. It is a manufactured product, the result of human ingenuity accumulated over decades. In principle, any country with sufficient capital, talent, and time could build a chip industry. But in practice, the knowledge, infrastructure, and industrial ecosystem required to manufacture the world's most advanced semiconductors are concentrated in a handful of places, built by a handful of companies, using equipment that only a handful of suppliers can provide. That concentration has, over the past several years, it's been revealed not as a footnote in the Trade Economist's Handbook, but as a structural feature of 21st century power. Governments have woken to this reality with a speed and seriousness that suggests they understand what is at stake. The CHIPS Act, the European Chips Act, the Japanese reindustrialization push, China's semiconductor mobilization, these are not normal industrial policy. They are responses to a strategic vulnerability that no major power is prepared to leave unaddressed. The question that will define the coming decades is not whether the chip war continues. It will. The question is whether the competition over semiconductors can be managed within the structures of international order through export controls, alliance management, and diplomatic engagement, or whether it escalates into something more destructive. History suggests that competition over foundational resources rarely remains merely economic. It tends, over time, to reshape the political world around it. Oil did not just fuel economies. It shaped borders, toppled governments, and drew the map of 20th century alliances. Whether silicon does the same in the 21st century is, in the most fundamental sense, still being decided in semiconductor fabs in Taiwan, in government ministries in Washington and Beijing, in the research laboratories where the next generation of chip technology is being quietly, painstakingly developed. The chip is small. What surrounds it is not. Strategic analysis helps us understand escalation, but understanding conflict does not mean wishing for it. History repeatedly shows that war, in any form, carries costs that extend far beyond military objectives. Economic disruption, political instability, and human suffering rarely remain confined to battlefields. Whatever the strategic calculations, the hope remains the same, that tensions are contained before they harden into open conflict, and that decisions made in the first hours prevent consequences that could last for decades, because in the end, no doctrine, no missile system, and no alliance structure can erase the long-term cost of war.